morning, Electric Culture of Safety Line Team. We're coming to you today in October 2024. It is a beautiful, wonderful morning here in South Carolina. We got Mr. Mark Forster here with ISPC, Institute for Safety and Powerline Construction. He is the director, senior director?
Director of Operations.
Director of Operations.
Yep.
So coming from Pennsylvania Power and Light and now with ISPC, I think Mark is a great choice for this position. He's doing a great job for them. First of all, a couple little things. Mark here, this is going to be, your third? Your third visit?
Yep, third visit.
He was here in June, this past June, and he gave a presentation called Structured Practice, and I believe personally that was my favorite from Mark. He does such a great job. Talked about substations his first visit, and wonderful. ECOS, today we have over 14,000 members, partners we call them, and around the nation, a safety coalition partnering up to ensure that our line team, they return home safely to their family crews when the task is complete. You can go to electriccultureofsafety.com and get more information and sign up and be part of this partnership. These webinars, we have 54 now, 54 that are all recorded, and you're welcome to contact me at safetytraining@bierermeters.com and ask me for which ones you want. You can see them on Electric Culture of Safety. Mr. Jeremy, our videographer, he's going to be putting on the promos, and you can contact me which one you would like to have for your cruise safety program to go over, which they're all great topics, every one of them uniquely different. So enjoy this time here. Mr. Mark, he's going to be talking about Back to Basics, Electricity 202, which is following Mark Turner, who's Mac Turner, who's the executive director of ISPC. So he had a Back to Basics Electricity 101. Mac did a fantastic job, had some action, little activity, some smoking. Literally some things were smoking during his presentation, and it's just a neat thing to remember. So Mr. Mark, he's going to go off from what Mac left. So Mark, appreciate you being here, brother.
Pleasure as always.
Yeah, appreciate it.
Yeah.
And talk to the folks, talk to us. Let us know about how Mark got into the electric utility industry. What happened? How'd that come about?
So, as most late teenage individuals, what am I going to do for the rest of my life, right? And so, right out of high school, I went in the military. Did that little stint, came out of the military, and then, do I go into the workforce? Do I go to school? What direction did I want to go? Originally, I chose the workforce. And back in the early 90s, I guess you could say the glamorous jobs weren't as fruitful, right? So went to work for a local grocery store in their warehousing, packing up skids to loading trucks and that type of stuff. Well, I did that for about 3 months and quickly figured out this isn't what Mark wants to do for the rest of his life, right? So enrolled in a technical college up in Pennsylvania, Pennsylvania College Technology, went there for electrical occupations. And then I started my career with Alcoa, the aluminum manufacturer, as an electrician and then a technician, and then ventured into my own business doing residential, commercial wiring, electrical, and then transitioned. My dad had worked for PP&L for, at that time he was still working, but he worked for them for about 37 years before he retired in the early 2000s. And so I kind of knew what I was getting into, and so I applied and was hired as a at that time they called them helpers, laborers, same type thing, apprentices, And so went through the training program there, became a journeyman electrician, supervisor, and then trainer. And then had the opportunity to actually work with Jimmy Vaughn,
Nice.
reviewing our temporary grounding policy. And so that's kind of how I got to meet ISPC, Mac, and Jim.
How long ago
and
was that about?
I guess
a while?
that, yeah, it's been probably at least 3 years, maybe even going on 4 years
Okay.
ago.
Yeah.
So got to know those guys. They invited me to I think it was the second annual trainers conference in New Orleans. So got to interact a little more with those guys there and learn a little bit more about what ISPC and T&D Power Skills was all about. And then probably about 6 months after that, I started to do some part-time work for them, consulting work.
Yeah. Affiliated. Right?
Affiliated consultant, yep. Went to the third trainers conference in New Orleans and kept kind of building that relationship. And then, Matt got his fishing rod out and, cast the line out and said, let me see if I can reel you in here. So it's been a journey. When you go from the utility world, right, into the consulting world, I just have that. I enjoy teaching. I enjoy sharing knowledge. And while I was doing that with a utility, you're kind of in that silo, right? So you're affecting that one entity. And I saw the opportunity through ISPC to broaden that footprint and share that information and knowledge and so on with a much larger group.
Right.
And so after it was probably about a 6-month back and forth between Mac and I, we finally agreed and got to a place where I felt comfortable coming over here, and so made the transition over to ISPC as their director of operations. So
Nice.
Doing a lot of things. For those of you that don't know or didn't see social media or aren't already a member of ISPC, we just last week launched a brand new website. So we have a brand new website out there that's been redesigned, much easier navigation for the user, tons more information. So you can check that out if you haven't seen that. A lot of good information out there. But yeah, it's just a constant evolution. So
Yeah, I highly recommend that you folks get involved with ISPC. Check out their website. Check out all their services. I was actually on their website last week, and I saw their post as far as their new website, the updated version, and it's beautiful. And there's a lot of information on it. And the website, the services ISPC provides, it'll help stir up your minds as far as if you have an area that you might be weak in your organization. It'll help encourage you to build those weak spots up so they become one of your strongest points within your organization. So highly recommend their services. Nonprofit organization, and I've seen Jimmy Vaughn's work. I've seen what they've done for Liberty Utilities, Centerpoint Energy, and I know Mark's developing a substation curriculum right now, and their product is, boom, must have. So highly recommend, and hope you all enjoy Mark's presentation today. Back to basics, electricity 202. The thing about Mark is he's very genuine. The utility industry is packed. I love it. The utility industry is packed with genuine people, and Mr. Mark, he's one of them, and it's good to know you, brother.
All right.
Good to know you.
Thank you, sir.
You bet.
Appreciate
God
it.
bless.
All right, good. All right, good morning, everyone. So as Brent was saying, today we're going to dive into the next series of Back to Basics, which is Electricity 202. We're going to do some review of some things that Mac went over when he was here a couple months ago and did 101. And then we're going to build on that. And this, I'm not sure how far this series is going to go, whether it'll be a 303 or a 404 or whatever the case may be. but we're going to, we'll take this as far as we think it needs to go to try to get the message across that, you know, in this industry we tend to, I don't know if I'd call it a rut, but we tend to get into specific types of work that we do in the industry. And then over time, as we go through our careers, and it happens to all of us, no matter what field really you're in, you become competent and confident, and unfortunately the next one is complacent, right? And we tend to forget the basic things that we need to understand and think about when we're doing our day-to-day task. And so that's what this series is really about, is bringing everybody back down to the foundational level and understanding when you're out there working, when you're building lines, when you're building equipment, putting equipment together, when you're installing grounding systems, all those things. What am I really doing, and am I creating traps for myself that as I'm doing that I'm not even recognizing, because we just don't, we tend to get this basic stuff early in our apprenticeship. And then, like Brent said, unfortunately, and it happens in our industry just as much as any other, as we go through our career and become that journeyman and further, we tend to think that, okay, I don't need training anymore, right? I learned what I had to learn, and now I'm good to move on in my career. And it's just not the case. We need to have that continuing education to keep us sharp and focused on even the most basic stuff. So this slide you saw in Electricity 101, so I just wanted to touch on it again, just kind of to paint the picture of where we're going. So, you know, electricity is part of our lives, right? Everybody, when you walk over to that wall and you flip the switch, you expect the light to come on, right? Everything we do relies on the power grid, right? If the power grid, we can see it now, you know, areas in North Carolina and Tennessee, and we have another huge storm coming into the peninsula of Florida later this week. And when those things wipe out power and wipe out infrastructure, it changes the way we live, potentially for long periods of time. I mean, you know, some of the damage that some of these folks have seen from this last storm, Helene, it could be months till they have their power back. So, you know, it changes the way we do things and the way we live. Our basic necessities are gone. And so, you know, electricity is one of the things that makes our world go around. When electricity functions as it's supposed to, everything's great, right? Everybody feels safe. They have power to do what they need to do, air condition their homes, heat their homes, lights come on, all those type of things. When electricity doesn't function as it's supposed to, normally bad things happen, right? Either we're out of power, or in our world, when we're building or maintaining the electric grid, when things go awry, it's normally not a good thing, right? We get into incidents and injuries and unfortunately, in some cases, fatalities. So it's crucial to understand what we're doing, and that it has to be done the right way every time. There can't be shortcuts. There can't be things that we skip in the essence of time. And as professionals in this industry, we need to understand how it is we need to work on this electric grid to keep not only the electricity flowing, but the electricity flowing efficiently, right? So, so we'll build on those concepts as we go through this. Again, just a little bit of review from Electricity 101. Obviously, Ohm's law establishes the relationship between voltage, current, and resistance, okay? Everything we do goes back to this mathematical equation, right? So voltage equals current times resistance, and if you're looking for resistance, it's voltage over current, and if you're looking for current, it's voltage over resistance, or divided by resistance, okay? So in everything we do out there during our work day and the tasks we perform, if you want to understand, right, what the available current is, or what the resistance is, or what the voltage is. It can mathematically be figured out in everything we do, from building circuitry to installing equipment to building our grounding systems, right? And this is the basis or the foundation for how that's going to operate. Okay. So a couple safety principles we'll touch on again that you saw in Electricity 101 that Mac did. Takes approximately 50 volts to break the electrical resistance of your skin. So every human being has a natural resistance to electricity, and the majority of that is in your skin. If the voltage breaks that skin, goes north of that 50 volt threshold, current is going to flow in your body, no different than it flows in the electric lines, right? And obviously that's not a good thing, right? We need to protect ourselves and understand where those dangers come from and understand what we need to do to prevent that from happening, okay? Again, referencing Ohm's law, plays a key role in determining the severity of the shock, right? So depending on the level of the voltage and the resistance to that voltage determines how much current's going to flow through our body should we break that resistance of our skin. So understanding how we make our resistance resistant to that voltage and that current flow is key to not being susceptible to electrical shock, okay? The higher resistance we have, right, dry skin, right, we're not sweating, those type of things, reduces the current flow, okay? If we're sweaty, if we come in contact with conductive surfaces, if we have cuts or opens on our skin, that increases our risk to that current flow. Okay, and so we need to understand that, right? If you got a cut on your finger, then that's an opportunity for you to be more susceptible to a current flowing in your body, okay? The current that flows through our body is a function of the voltage, like I said, and the body's resistance. So 50 volts is roughly the threshold that will break the resistance of your skin and allow current to flow in your body. Obviously, this isn't rocket science. Current passing through your body, hand to elbow or, hand to foot is going to be less of a problem than hand to hand, because if you're part of that path from hand to hand, you're going through your vital organs in your body, right? And you're going to take or have the opportunity to have a much more, critical shock incident, right? Because you're going through your organs. You all saw when Mac did his presentation on 101, he did the electrical simulation with the pickle, right? And that's exactly what happens internal to your body. If you become part of an electrical circuit, it's going to start cooking stuff internally, and normally is not going to be a favorable outcome for you. So the second safety principle is current flows in every path inversely proportional to the resistance in that path, okay? So if you are, depending on your resistance, when you get yourself in that circuit unintentionally, depends, and the other resistances within that path. We normally think of this in our grounding setups, right? That if you are part of that circuitry, current's going to flow through you as well. And depending on the resistance in your grounds and your bonds and so on, is going to make a difference in the amount of current that flows in you. Okay. So, electrical shock occurs when a person becomes part of an electrical circuit, right? And we need to understand that so that we can keep ourselves from becoming part of that electrical circuit. The severity of the shock depends, we talked about the current, the duration of the contact, right? So Everybody, maybe not everybody, I've done it many times. Most of us in the electric field have. You know, if you're changing that light switch on the wall, we've all got zapped, right? And that's a quick, oh dang, right? Well, normally when you get into our world in the high voltage spectrum, you can't let go, right? There's normally enough current there that now I can't let go, right? So now it becomes duration, right? How quickly does the relays isolate the system, right? And so, and then obviously the path through the body is the last key there, okay? We already talked about flowing through vital organs. It's going to be far more dangerous and unfortunately a lot of times end up in a fatality, okay? Our electrical grounding, I like to reference, so grounding and bonding is an easy way to relate this stuff where it kind of sinks in and they can connect the dots to make it, to make that connection between resistance and current and voltage. So you'll hear me several times throughout the throughout the presentation, and even at the end we'll talk a little bit about your grounding setups and what goes on there. But it's just an easy way to relate all of these together that people do day in and day out. We install grounds and bonds on our work areas day in and day out. And so it's an easy way to relate between these. Okay. And then the last safety principle that we learned in 101 was that if you insert a resistance in a current carrying grounded conductor, a voltage rise will appear. Okay? And again, that voltage will be proportional to the resistance in the path. So that's the third principle that you learned in 101. This was covered in 101 as well, ground potential rise. So anytime we install a ground, right, in an electrical system, if current flows, there will be a voltage rise or a potential rise in that circuit. As we install more grounds, the second ground and third and so on, we then create a path in our grounded conductors for current to flow. So if you have induction or you have a fault or any form of induced voltage, current is going to flow in that circuit. And that's okay as long as you understand that and don't become part of that circuit or break that circuit and you now become the new path for the voltage and current to flow, right? And then based on the resistance in those grounded temporary grounds depends or is proportional to the voltage that you're going to see in that pathway, okay? And you can see here the resistance in ground number 2 is higher than the resistance in ground number 1. You're going to have more of a voltage rise in that higher resistance ground. And we need to understand that. In this case, if you become part of that circuit, one circuit, it might not be that bad. If you get between these two grounds, that's where the voltage or the potential difference comes and you can be injured. So just things we need to understand about current flow, not only in normal in-service conductors, but also in our grounding setups. We need to understand where current will flow and what the potential is there and how we keep ourselves from becoming part of that circuit and what the resistance of that circuit compared to us is so that we are not the ones that get injured. Okay? Every ohm of resistance you build into your protective grounding system raises the voltage across your body. And so I recently did a class a month or so ago, and I'm not going to say where I was at. It was a crew best practice presentation. And so I asked the class that I had, we were talking about PPE, we're talking about grounding, we were talking about all kinds of things. And I said, so how many of you religiously, before you apply your grounds, clean the surfaces of the conductors before you install your ground, right? To make a good, solid connection. Nobody's hand went up in that class. And I said, why? There really was no good answer. It's those shortcuts that we take that can lead to problems down the road, right? And unfortunately or fortunately, I think the basis for that is very little incidents happen because of me not cleaning the conductor before I place my temporary ground on there, right? Me not cleaning the conductor before I make a crimp connection on a wire or on a switch, right? But those are all things that build resistance into that circuit. And, you know, as those conditions build and multiply, it becomes more and more likely that it could create an incident in the future, right? So when it comes to us and our grounding systems, we want to control the voltage. If we control the voltage, remember we said that 50 volt threshold, if we control that voltage, then the current doesn't matter, right? Because it can't break our skin if we keep the voltage low enough, okay? As we said a little bit ago, the human body has natural resistance to electricity, and primarily in our skin. Most of the calculations that our industry does and what OSHA bases that resistance value on is 1,000 ohms, okay? You can be anywhere depending on your body makeup and you know, there's a lot of things that go into account there. You could have resistance up to 100,000 ohms, okay? But like I talked about a little bit ago, when we start bringing things into moisture, sweat, open cuts on our hands, all those things, that resistance could drop down to as much as 100 ohms, okay? And so then you are much more susceptible to an electrical shock, okay? Reduced resistance increases the current passing through our body. So, you know, obviously we want to be closer to that 100,000 or well north of that 1,000 ohm value to make ourselves as resistant as possible to that electric flow. And obviously there's things we do in our daily jobs to make that happen, right? PPE and things like that we use to increase the resistance of our body so that we don't become susceptible to that current flow. Okay. The average fatal current is about 100 to 200 milliamps. So, you know, that's not even an amp, right? We talked a couple times about just the normal wiring in our house, right? The least current circuit in your house is 15 amps, right? And it goes up from there. So you can see, you know, you get shocked on that receptacle. Depending on the load on that circuit, could be a problem, right? So 100 to 200 milliamps, very, very low amount of current that needs to flow to potentially be fatal, okay? So you can see here, if a worker's resistance drops due to sweat, compromised PPE, cuts, things of that nature, this is just an example. The current, 1,000 volts, right? We're all out there on the systems we're working on are well over 1,000 volts, right? Even your normal distribution circuits, 12,470, that's 7,200 to ground. Far higher than the 1,000 volts we're using here as an example. And if you're right at that 1,000 ohm threshold as far as your body resistance, you're going to take 1 amp through your body. More than likely going to kill you. So it doesn't take much here, and that's the thing to understand. And again, going back to what I said a little earlier, we tend to, as we work with this stuff over time, I mentioned earlier I worked at Alcoa early in my career. Our low voltage there in that industrial plant was 480 volt. And over time of working with that 480 volt, you get the false sense of security that, oh, it's only 480 volt, right? It's not, you know, 12,000 volts. It's not 130,000 volts, whatever the case may be. And so you tend to not think about that 480 volts even at 480 volts, you're going to have enough current to flow in your body and do damage. And here's an example of that. So a utility worker in contact with a 480 volt panel, okay? Perfect resistance, 10,000 ohms. You can see here, 480 volt divided by 10,000, you're still going to get 48 milliamps. You're halfway to that threshold I just showed you a couple slides ago that can be fatal, right? And then if you lower your resistance, okay, with that same 480 volt contact, so now we're down to that 1,000 ohm threshold that we've been talking about, that current jumps up to 480 milliamps. Right? We just said the fatality threshold is 100 to 200 milliamps. Well, now you're double that, just because your resistance went from 10,000 to 1,000. So that's how narrow of a window we're playing in between just getting shocked or potentially being killed. And we need to understand that, and we need to understand those conditions that, if they change, can potentially be fatal. Okay, so let's break down the relationship a little bit between resistance, continuous current, and potential difference or voltage. And we're going to look at it again just because I think it's the easiest way for us to relate to it. We're going to talk about these things in relationship to our temporary grounds. It's just an easy, I just feel it's an easy way to put one and one together, right? So a couple things resistance depends on, right? The material's properties, right? Obviously copper is a very good low resistance conductor when it's clean and everything is the way it should be, right? The length of the conductor, and we're going to talk a little bit more about that. Obviously the longer the conductor, right, the higher the resistance. How thick the wire is, right? Thicker wires have lower resistance. Thinner wires have less, right? Less cross-sectional area for the voltage and the current to flow. Temperature plays a key part in this, as well as obviously the current flowing in the conductor. So we'll build on this a little bit here as we go. So current flow and conductor resistance. So this is an example. You can see the conductor on the bottom is a copper conductor. The conductor on the top is iron. And you can see the electrons flowing. And you can see the resistance or in the iron conductor is much greater because of temperature and other things, and doesn't have as good a resistance as the copper does. And so what happens when the current flows through these conductors, right? So higher resistance, less current flows, more voltage drop. So if you become part of that circuit, okay, where you have a higher resistance, we always talk about our grounding systems and so on should be as low a resistance as possible, right? Because we're trying to keep that voltage drop as low as possible. If you open up that grounded circuit and you become part of that circuit, the higher voltage drop, obviously, the more risk it's going to be to you as an individual. Lower resistant, more current flows, less voltage drop, okay? Again, control the voltage, the current doesn't matter, okay? And then obviously friction and heat, right? So dirty connections, high resistance conductors, those type of things create friction and heat, okay? Heat affects the resistance, friction creates the heat, all bad things when we're talking about a efficient flow of electrons through our conductors. All right, continuous rated current refers to the maximum current that a conductor can carry, okay, without exceeding its temperature rating. So all conductors have, a max current that the current they can carry, okay. Again, most people 2-aught AWG wire is commonly copper. It's this. On the line side, on the overhead side, underground side of our system, is normally the standard size temporary ground that we use, right? 2-aught. Get into the substations, it jumps up to 4-aught. 300 amps is what that 2-aught ground can carry. So you know, we talk about the resistance of our grounding systems, but the other thing we have to keep in mind is it's not just the resistance of that conductor, right? You could take that 2-aught ground and cut half those strands of wire going through that conductor, and I can still have a low resistance conductor. The problem is now I no longer have a conductor that can carry 300 amps. So should a fault occur on the system and my ground is not both low resistant and able to carry the current that it needs to carry to take that voltage to ground and you know, have the protective relays respond to it, you could be setting yourself up for a very bad day, okay? Voltage drop, the reduction in voltage as current travels through a conductor due to its resistance, right? So we saw that in that relationship between the iron and the copper conductor there. The higher the resistance, you know, the higher the voltage drop you're going to get across that conductor. The voltage drop's directly related to the resistance of the conductor and the current flowing through it. Again, you can figure that out easily by using Ohm's law. The other thing, and I talked a little bit to Mac about this and some other people, it's amazing to me. If you go, I can almost assure you, if you go out to a crew today in the field and ask them to tell you what Ohm's law is and what it means, you're not going to get probably over 50% that understand or can tell you verbally, one, what is the formula for Ohm's law? And number two, what does Ohm's law do, right? It's the relationship between voltage, current, and resistance. And it's one of those things we've all learned in this field. It normally just is one of those things we learned very early in our apprenticeship. And then it tends to just go to the back of our mind and in most cases right out of our mind, right? And so that's a bad thing. Obviously the voltage drop must stay within certain limits to ensure that equipment operates quickly, correctly, and efficiently, okay? If the voltage drop is so high, it could potentially not allow those relays to operate quick enough in the case of whether it's induction or a fault or lightning or whatever the case may be that energizes our protected work area, okay? Most installations, the voltage drop maximum 3 to 5% of the system voltage, okay? So that's a very, you know, if you're talking 12,000 volts, 69,000 volts, you know, that's not a very large voltage drop allowable. So back to that statement I made just a little bit ago, resistance value must always be considered in conjunction with the continuous current that the wire can carry, okay? Again, resistance, you can still have very good resistance, right? When we test our grounds, you know, you can't just take an ohm meter and go from end to end of my ground. I could have one strand out of that 2-aught conductor that's connected and the rest can be broken, and I'm going to get good resistance. There's going to be resistance there because there's no current. But obviously as soon as I bring current into the equation, obviously that one strand isn't going to carry any current, right? So we need to think not only in our grounding systems keeping them as low resistance as possible, but it also needs to be related to the continuous current that that system can carry without failing, okay? If the resistance is too high, the wire experiences greater voltage drops, okay? We've already said the material and the length of the wire directly affects the resistance. And then here's a kind of a breakdown. This is a standard 2-aught temporary ground, 15 foot long, you know, probably one of the most standard grounds that's on almost every line truck in our industry, right? So you can see here, this is just strictly resistance value of that temporary ground, right? You can see the ohm value that you get there, all right? So voltage divided by the available 300 amp current, there's where you should be if you just went across it with a voltmeter, okay? Obviously we don't test our grounds like that, right? Bierer Meters has a grounds tester, and they apply current to that ground and then take a reading, right, to get you to a satisfactory value. Something we haven't talked a lot about, I think Mac might have just touched on it in 101, but the other thing along with resistance is impedance, right? And so that's the effective resistance in an AC circuit or component to AC current, okay? It's arises from the effects of ohmic resistance and reactance, all right? So reactance is the non-resistive component of impedance in an AC circuit, and this arises from the inductance or capacitance or both causing current to be out of phase with the voltage, okay? And I'm not going to build a whole lot more on impedance reactance. I just wanted to kind of show everybody or mention that they're present in our AC circuits. You know, induction, whether you're talking a fault, whether you're talking a re-energization of a circuit, whether you're talking induction in a circuit, it's all AC, okay? So it's just important to understand it's there and what it does, okay? So let's talk about phase to phase and phase to ground faults, okay? So the voltage difference between two phases is higher than between phase to ground, okay? So OSHA says that when we're working on multi-phase circuits, we need to short circuit those conductors, right? Short circuit is phase to phase. That's what they're talking about, not phase to ground. You can go phase to ground, phase to ground, phase to ground, right? And yes, you're going to short circuit it, but is that the best way? Okay, and I'm going to show you here that it's probably not the best practice. Will it get the job done? More than likely, yes. But because of the high fault current, your protective devices are going to operate about twice as fast if you are short-circuited phase to phase, okay? Normally about 2 to 3 cycles, okay? A cycle's about 16 milliseconds, just a little over, right? So very quickly, if you're grounded phase to phase to phase in a fault and then to ground, your protective devices, and that's really what we're trying to do. The grounding and the bonding, we talk about it, and I think a lot of times it gets used, the statements get used incorrectly, right? Grounding is not really there to protect you, it's there to protect the system, right? Bonding protects you by eliminating differences in potential. Now you can install your grounds in a equipotential bonded fashion where it's protecting the worker. But really what those grounds are there to do is to, one, isolate the fault, whatever it's coming from, induction, accident, re-energization, whatever the case may be. And then the bonding or the equipotential setup is there to hopefully minimize what you as the individual sees when it comes to current flowing in that situation, okay? So the quicker we can clear that fault, the better chance we have of not being susceptible to that current flow, okay? So here's another calculation, fault current based on a line-to-line voltage of 12,470, right? A very common voltage that we work on in our distribution systems, right? It's also based on the impedance of the system, and then the transformers, conductors, and protective devices, right? It all plays into the equation of how much current you're going to be susceptible to. So assuming just a standard 10 MVA transformer with a 5% impedance, okay? In order to figure out what fault current could be in that configuration, should something happen, you take the voltage line to line divided by the system impedance, right? So 12,470, you divide it by that 5% impedance, which is 0.778 ohms, and you can see that the fault current in that situation is going to be north of 16,000 amps, okay? We said it takes 100 to 200 milliamps to kill you, right? If your grounding system and so on is not configured properly, you're not surviving that, right? this fault, I had an instance, just a little side note here. So I went, we talk about current or faults in a fault like this, phase-to-phase fault. I was doing a job walk down at a substation several years back when I still worked for the utility. And I was in the substation doing a field walk down for a future job coming up. Perfectly sunny day, just like we have here. It was probably about 65 degrees out. Perfect conditions. And I'm standing right outside that substation and sitting in my truck, actually. I was pulled right up along the fence. You know, I was probably a little closer than here to the wall, the tent there. And I was typing an email back to my scheduler to say, hey, everything looks good. We're good to proceed with this job. Go ahead and push it through. A 10-inch standoff post insulator, we assume, we're not 100% sure, but we assume just from examining the after effects, had a hairline crack in it. And just to that instance that I was sitting there, that voltage tracked to ground. And we had a phase to ground fault. And I'm going to show you the calculation for a phase to ground fault here in a minute. Just similar to this phase to phase fault. The bus section of the substation in an instant had probably about a 20-foot round ball of fire. My window in the passenger side of my truck was closed. I could feel the heat through the side of the truck. It vaporized the neutral connection from the XO bushing on the distribution transformer to the buswork, 4-aught copper wire, probably about 10 feet long, vaporized. We could not find a piece of it. That's how high the fault current was, right? So these things are real, right? If we were working near that, you know, who knows what would have happened, right? Luckily, everybody was far enough away from it when it happened. But, you know, the thing that we need to understand is we don't know when a fault's going to happen. We don't know when somebody's going to accidentally re-energize a circuit, right? It's hard to determine what level of induction or induced voltage you may have in your grounded circuit when you're working. We don't have the ability to figure out or determine when all these things are going to happen, right? That's why they're incidents or accidents, right? And so the only thing we can do as workers is every single time build our grounding systems, do our connections and our conductors the right way every time. It's the only way we can, you know, hopefully prevent ourselves from being part of that. So here's the same example, just going phase to ground instead of phase to phase, okay? So again, your line to ground voltage, well actually that's your line to line voltage, 12,470. Your line to ground voltage, 7,200. Okay, impedance of the system, all the same. Taking that same 10 MVA transformer with a 5% impedance, okay? So you take your voltage line to ground and your impedance of the system, 7,200 divided by that same impedance, you're still over 9,000 amps in that case, okay? So you can see when a fault occurs, the kind of current, you know, we just said your 2-aught temporary grounds are good for 300 amps, right? Well, they're not going to sustain a 9,000 amp fault. You're going to vaporize them, right? So the key is the grounds need to be able to carry enough current to allow that 2 to 3 cycles to trip those protective relays off, right? That's the key, okay? So the other thing we've talked about a little bit is length of cable, right? And so the longer the cable, the longer the resistance. Well, the other thing that happens when it comes to length of conductor when we're talking about our grounding that we install for our protection is not only does that length of cable increase the resistance in our grounding configuration, but it can also cause mechanical damage, right? And I'm going to show you some examples here in a little bit of where grounds are applied for the protection of personnel, right? And to get the system to trip off as quickly as possible should there be a fault. But due to using long cables and not securing them properly, you're going to see the violence that occurs when that fault happens, right? And so, you know, you always hear when you install your grounds, and OSHA tells you this, your cable length should be as short as possible, right? And, you know, the answer you always get is, well, 15 feet's the shortest ground I carry on my truck. Well, when you see some of these videos of what happens to a ground in a fault condition, should you have excess cable that can flail and swing around in a fault, it may change your mind a little bit about, oh, well, maybe there's a job we do a lot that maybe we need to get some grounds made that are shorter so that we don't run into these scenarios. So this is a parallel 2-aught phase to ground 3 times. So phase to ground, phase to ground, phase to ground. So we just talked about how short circuiting phase to phase to phase, then one conductor to ground will clear a fault a little quicker. Let's take a look at what this is going to look like when this fault happens. Pretty violent. You know, if you're in that work area working on that equipment there and that fault occurs, yes, it tripped the system off very quickly, okay? But the violence and the mechanical energy in that fault may not be sustainable by a worker, okay? So the next one, this is single 2-aught phase to ground. So this is how we're talking about phase to phase, and then one phase to ground, okay? So because of doing phase to phase instead of phase to ground, you can see that the explosion was less violent, right? But you still had grounds flying around, right? They still broke, they still flailed around and created that mechanical hazard, okay? And then the last one we're going to look at, in this instance, they secured that extra ground just by some ropes and loosely tying those things. You don't want to tie them tight. You don't want to coil your grounds around steelwork. I've seen it happen, right? Well, I'll just connect my ground to the ground and then I'll go around the steel a couple times and go to my conductor. Well, you just created an inductor, right? A coil is what you just did. It's going to be a problem. So we don't want to do that, but you'll see in this video that they just structure around the ground, structure, just to keep it from moving quite as violently. Much, much less violent mechanical movement, right? And so just an example of how we can, just by installing these little ropes to hold those grounds, kept them from blowing around and flying all over the place, creating a mechanical hazard. We talked a little bit about equipotential zones, right? And OSHA tells us we have to install our temporary protective grounds in locations and arrange them in such a manner that it prevents the employee from being exposed to hazardous differences in electrical potential, okay? So I had a great conversation with a group I was doing some training at a couple months ago about this, and we kind of got in, not to an argument, but we got into a very good debate of bracket grounding versus equipotential grounding, right? And so the key importance that we got to at that training class, and the point that I want to make here is, how we install our grounds potentially could help us or hurt us in an incident, right? And so bracket grounding, we've all done it, right? It was the way we did things for years and years and years, right? And we thought it was good enough. And then people started to do some research and so on into why are people getting hurt when incidents happen, right? Faults, induction, whatever the case may be. And we realized, right, we said earlier, one of our safety principles, number 2, that current flows in every available path, right? So you can see here, you have a guy working on the center pole there, and you have your bracket grounds installed on either side of the worker. But whether it's induction, whether it's a fault, whatever the case may be, voltage and current are going to flow obviously in both your conductor and your neutral. It's going to flow through your bracket grounds, and depending what you're touching as the worker on that pole, it's going to flow through you as well, right? And then obviously through your grounds to ground, right? So you're going to have current flowing everywhere in this configuration, okay? Inversely proportional to the resistance, right? So very important that you understand this, right? If you're doing this bracket grounding, okay, and I know for a fact, including the utility I worked for, up until equipotential grounding became a thing, back in 2014, I think it changed in the OSHA regs that we had to equipotential ground. At the company I worked for, if you had this setup right here, you bracket grounded, out de-energized, bracket grounded, you could work in leather gloves. You didn't need your rubber PPE, okay? In an incident, that's probably not going to be good enough for you, right? And so, you know, now we're required, where reasonably possible, to install our grounding in an equipotential fashion, right? So now, this is all assuming that all your conductors are intact, right? Obviously, if you have broken neutral, broken phase wires, those type of things, you're going to need to install some bracket grounding until you get to certain points, right? You may need to wear your rubber PPE. You may need to use you know, max or temporary jumpers as you're going to make connections of your conductors or reconnect your conductors, right? And then once you reestablish your conductor paths again, now you need to turn from that bracket grounding to equipotential grounding if you're going to work on it de-energized and grounded. Obviously you can work on it and treat it as it's energized and wear your rubber PP, and so there's multiple ways to skin this cat, right? But you got to be aware, and you got to understand what the risks are and what the potential hazards are, so that you can make the best choice of how to protect yourself, okay? And then again, you know, since 2015, we've been required by OSHA to install our grounding and bonding in an equipotential fashion, okay? Again, in order to do this, all your conductors have to be intact, right? If you have broken conductors, you can't equipotentially ground at that point, okay? So we just need to understand that. If we do this, we put all the conductors and the pole at the same potential, little to no current is going to flow through the worker, right? In a fault, it's going to all go to ground, okay? So just some things we need to understand there. Same thing in a substation, right? If we install bracket grounds here right now, okay, looking at this picture with those 2 bracket grounds installed, the only potential place for a difference of potential is at the open contacts internal to the high voltage cabinet of the breaker. You can see the contact right here, right? Breaker's open. That's your only point of difference of potential, where you're not going to get across that because it's internal to the breaker, right? But should you be disconnecting this circuit breaker, say for removal or replacement, right? And as soon as you take the leads off the breaker, now you've just created some differences of potential, right? And so it's understanding that there's a potential there for a hazard, okay? I'll be the first to admit I've done this 100 times, okay? Because I didn't know any better, or I didn't think about it, or recognize that, hey, by unhooking these leads to the breaker, I just created a difference of potential. Now, as long as there's no fault, as long as there, you know, normally you're going to have disconnects open here on either side of this breaker, right? So the only issue here may be induction, right? If there was a fault out on a line or something, or even internal to the sub with the open disconnects, which just doesn't show, you're going to have that open point, right? But it's understanding what configuration you have, right? And what you need to do to eliminate that difference of potential. You know, this ground also could go from here down to here, would do the same thing as jumping across it like that. But it's just understanding where those potential hazards are coming from and how to protect yourself, right, in those instances. All right, so this is a slide that is present in most of our grounding and bonding presentations, but I thought it was worth just kind of reiterating again, you know, how to, a couple recommendations of how to protect yourself when you're installing your grounding for your protection, right? So we talked about it, understand the sources of current flow, right? Understand if something does go wrong, where's current going to flow in this system I just installed grounding on to protect myself, right? And make sure that you have your grounds and your bonds installed properly to minimize, you know, that potential. Understand the paths that are available, right? Including you, you're a path. Depending what you're touching, when a fault or induction or an accidental re-energization happens, understand where the paths are that voltage and current can flow so that you can protect yourself from those, okay? And again, you're one of those paths. Understand how to bond in or how to isolate or insulate yourself, right? So there's multiple ways to protect yourself: grounding, bonding, PPE, isolating conductors so they're not even connected to the system, right? There's multiple ways to protect yourself. It's just understanding which one works best in which situation to keep you as safe as possible. And then understand the limitations of the method you chose, right? PPE is only good to a certain voltage level, right? If your PPE, you know, the other thing that kind of blew me away, maybe it didn't, but in that same crew best practice class I was doing when we talked about PPE, I asked the class, how many of you faithfully, every time before you don your PPE, do you inspect it? I had one hand go up out of 22 individuals. I'm like, why? It's your protection, right? You're relying on that PPE to protect you. Why would you not take the 10 or 15 seconds to roll your glove up and make sure it holds air, right? Or look over your sleeves and make sure when you threw them in the truck bin or wherever you store them on the truck, you didn't accidentally slice it or they're not dry rotted or whatever the case may be. Why would you not do that? It's your protection, right? And so these are the things that are going to protect us when voltage and current flow in our protected systems, okay? So I'm going to end this presentation with the same slide that ended 101 just because it's all relevant. So the things we need to remember: electrical incidents are serious and can even be fatal, right? We need to understand the hazardous positions that we put ourselves in and what we need to do to protect us so that, best case scenario, the incidents never happen, right? But again, like we said before, we don't know when a system's going to be accidentally energized or a fault's going to happen down the road, and if all the conductors are intact, you're going to see current in that system and voltage in that system, right? The neutral is throughout the entire system, so as long as it's intact, a fault could happen 5 miles down the road, you're going to see some sort of current at your work area. It's just, that's the way it is, okay? Even the most trained and experienced workers can make mistakes, okay? This is back to basics, right? We've done 101, we're now doing 202. We need to keep up on our training. We need refresher training. It doesn't matter how long we've been doing this. I can tell you multiple incidents where, you know, people, well, hey, what happened there? Was that one of the young guys? No, it was one of the guys that's been here 35 years, made a mistake because he got complacent, right? So we all can make mistakes. If you ever get to that point in your career where you think you can't make a mistake, I would ask that you just find a different line of work to work in, because you're going to be the next statistic that we're talking about, okay? By knowing, remembering, and practicing basic electrical principles, we can prevent incidents, okay? So, you know, all the stuff we talked about on 101 and all the things we talked about today in 202 can all be put together and used to help you make better decisions about how you're going to protect yourself when you're out there working, right? And, you know, we talked a lot about your grounding setups and cleaning things and making sure you have good connections. It also goes into the work that you do every day, installing and repairing the electrical facilities out in the field, right? If you're not cleaning those conductors when you're putting them together or building them, that all builds resistance into that system that someday is going to be part of somebody's work area. And maybe their ground connections are good, but maybe the connections out on the line or in the facilities that you're working on are not good because somebody didn't install them properly clean them, properly crimp them. Everything goes into working to help keep you safe. One, keep the system running efficiently, and two, keep you safe when you're out there working on those systems. Every little bit, we said every ohm of resistance that you build into your protection, well, when you install grounds on the system, the conductors are part of that circuitry, right? So if they have a high resistance, that's going to be included into your grounding protection. So it all counts. It's not just one little piece. So I can do this right and I'll be good. Doesn't matter if I do this right. No, it all works together. It all has to be done properly every time. Okay? Electrical injuries, even when not fatal, can be devastating, right? I told a story, I believe it was the first time I was here when I did my substation presentation about a friend of mine that was burnt really bad, right? And none of us really know how he survived that. I guess God's will, because he went hand to hand and took 13,000 volts right through his heart and all his major internal organs, survived it. But today, I think it's the right arm he's missing to his elbow, and on his left hand he has these two fingers left, right? Changed his life forever. Was 30 days from retiring, right? Looking forward to it, going to travel with his wife and go do all kinds of things in retirement. Changed his life forever, right? So, you know, even if these things don't kill us, they can be life-altering. And not just to you, to everybody around you, right? A lot of things that he used to like to do, ride motorcycle, all kinds of things he can't do anymore. You know, I'm sure there's a lot of things his wife has to help him do because he just can't do on his own anymore. You know, we need to think about this stuff when we're out there working. All electrical incidents are preventable, okay? Probably about 10 years ago, 15 years ago at the utility I was at, we started the transition from the safety department, right? And everybody's thinking that everybody's safety was the responsibility of the safety department and the safety men and the safety professionals, to now I think where we are in today's industry that your safety is your responsibility, right? You're responsible for your own safety and the safety of your brothers and sisters, right? But you can't be in charge of their safety if you can't first be in charge of your safety. So when they started preaching all the incidents are preventable, everybody's like, yeah, everybody's going to make mistakes. Everybody's going to have accidents. Yes, we're human. We're fallible. We all make mistakes. But when it comes to electrical incidents, right, everything we've talked about in 101 and 202 can go a long way to helping you understand how you need to work day in and day out to prevent electrical incidents, right? You might make a mistake, but hopefully the outcome is not, you know, devastating or fatal like we just talked about. And then it's our responsibility to know and implement basic electrical principles, right? We're all professionals. We need to be held accountable, right? If you make a mistake, just own up to it again. You know, we all make mistakes, but we're also all professionals. So we need to understand what we need to do to keep ourselves safe, keep the lights on, keep the electric flowing, and, you you know, at the end of the day, everybody's wish is to come to work, make a good living, and go home at the end of the day and be able to do the things that we like to do. So thank you. My contact information is there on the screen. If you have questions or comments, you know, give me a shout on the phone. There's my email address, mark@ispconline.com. Reach out to me. I'd be happy to you know, discuss anything with you. Again, I want to appreciate ECOS and Brent and everything they do here at Bierermeters for our electric industry. I think, you know, we're starting to see the fruits of our labor, you know, helping to, you know, everybody that comes here and does these presentations is just trying to give a little bit back to the industry that, you know, that has given so much to us. And I think it's a very valuable resource and important need in our industry that we continue to educate people and give them the knowledge and the tips and so on to keep themselves safe while we're working in the field. So thank you, everybody, and we'll see you next time.